now we come back to theorem dpq is greater than or equal to 0. Proof. Negative dpq is equal to negative the sum over all values of x, p of x, log p of x over q of x, which is equal to, I can take this negative inside the log, and what does that do? That's right, it's the inverse, so q of x over p of x. Because log is concave, this is now less than or equal to log, excuse me, this can be interpreted as the expected value of log q of x over p of x. Since log is concave, this can be interpreted as this becomes, I can take the expectation inside the log and apply this, and I say log expected value of q of x over p of x. Which is equal to what is the expected value of q of x over p of x? This is log the sum over x, p of x, times q of x over p of x. So those cancel, and I get log sum over x, q of x. What is the sum over x of q of x? It's 1, because q of x is a valid probability, so the sum over all the possibilities is just 1. So this is log 1, which is what? 0. So log base anything of 1 is 0. Okay, so let's trace this back. 0 is equal to that, blah, blah, blah. So I have minus dpq on this side, less than or equal to 0. So therefore, if I multiply both sides by minus 1, dpq must be greater than or equal to 0. Okay, in the statement of the proof, I said this is true with equality if and only if p of x equals q of x. I'm not going to show the only if part, but the if part can be seen if p of x equals q of x. Then what do I have? I have that, well, obviously, p of x over q of x, if they're both equal, that's always equal to 1. Log of 1 is 0. Sum over p of x of 0 is just 0. So dpq is equal to 0. So that's the if part. The only if comes from Jensen's inequality, and we won't show that. So in other words, it's a distance, dpq is a distance in the sense that if these are the same probability density function, then the distance is 0, and otherwise the distance is positive. final thing I want to show today, theorem, h of y given x is less than or equal to h of y. This is the statement that I started the class with. Proof. H of x, well, what I'm going to do, excuse me, not h of x, h of y, what I'm going to do is I'm going to take this to the right, and I'm going to say h of y minus h of y given x. Let's substitute for the entropy here. This is the sum over all possible values of y, p of y log 1 over py, minus the sum over all values of x and y of p of x and y log 1 over py given x. I can take this minus inside over here, sum over y. Actually, I'm going to do two things in this step. Firstly, it doesn't matter if I sum over both x and y of p of x and y log 1 over py. This comes out to the same thing. Even because this is not a function of x, summing over x here will just result in p of y. That's a property of probability, that if I have a joint probability density function p of x and y, and I sum over x, I just get the probability of y, the marginal probability of y. So this makes no difference. I can certainly do that. What I'm going to do over here is I'm going to take that minus inside. If I take that minus inside the log, what happens? This just goes to the top. Okay, next step. What I can do now is, because these are both sums over pxy, I can just collect those. So I end up with sum over x and y, p of xy, log 1 over py. Again, I'm going to do two things in this step. So first thing I'm going to do is I collected those. The second thing, I'm going to restate this as, what's py given x? It's just, remember this from last time, p of x and y divided by p of x. Okay, next step, sum over xy, pxy. Adding together these logs is equivalent to multiplying, so what I end up with is log p of xy divided by py dx. Can anyone see how to finish the proof? So we spend a lot of time showing this. So that should be a hint.